This video is an introduction to the orbits function of SpeckleToolBox version 10.03. Now, first of all, you'll need to download the files for the program, and I would suggest putting it into its own folder, as I've done here. It may come as a zipped file, and you just have to extract all the files present. You should end up with 5 files. Here we have the application file, SpeckleToolBox. We have this other file here called ORB6 orbits. If we open this file, and you can open this up with a text editor, for example, Notepad, this file contains the orbital parameters of all the systems listed within the 6th orbital catalogue. Just a couple of points I want to draw to your attention. Let's have a look at a star system called STF42AB. So you can't find it. You have to be very careful with the spacing of your searches within this file. So we'll just go and find that again. Here it is here. Now you'll notice here that there are 2 entries for this system, and that's because there are 2 proposed orbits for this system. There's one by Kiselev in 2009 and one by Ismailov in 2019. Now SpeckleToolBox will go only to the first orbit here and display the parameters associated with that orbit. If you want to study the second orbit, then you'll need to manually delete the parameters associated with the orbit that you're not interested in. Fortunately, this doesn't happen too often. Now, the other point that I'd like to raise is that the orbital parameters associated with some of these systems may be out of date. So let's have a look at, for example, Dunlop 5, which we're going to go into in greater detail. There's Dunlop 2, there's Dunlop 5. Now you can see here that there's one entry and that there's an orbit that's been proposed in 2018. If we go to the historical data file on Dunlop 5, this is what you should be getting from the Washington Double Star catalogue. These are all the measurements over the years. And here we have the orbital elements. You'll notice here for Dunlop 5 that there's an orbit which has been proposed by NAP in 2020. So the orbital parameters that are present for Dunlop 5 here need to be corrected. Now the way to do this is to go to the 6th orbital catalogue of visual binary stars. So we'll go to the 6th catalogue. Here we go. Search here. So we have the 6th catalogue of orbits of visual binary stars, and if we come down here, we've got orbital elements. You'll notice here there's an SQL file. So just download that. And if we open up that file, that should have the up-to-date orbits function. So let's search for Dunlop 5. And you'll notice here, Dunlop 5, going across. Here we've got the orbit for 2020. So I would copy that, just highlight it. Copy. I would go to the, close it. I would go to the orbit here, the old orbital file. Just put in space, paste. And you can see here we've got both orbits present here. So what I would do is delete the old orbit of 2018 Also just get rid of that space beneath it. And that should have the updated orbital parameters associated with Dunlop 5 present in it. So I would save that file. Okay, I would close this. Close that. Now let's go to the program itself. You'll get a message saying Windows has protected your PC, more info. I would run anyway. Norton may come up or your antivirus may come up. With this, I would allow the app. Okay, so here we have the orbits function. So we're going to click on that. Now we're going to read the observation file, and the observation file it's going to read is the historical data file from the Washington Double Star catalogue. So let's open that. And here we can see the apparent orbital ellipse with all the data points present here. Here we have the orbital parameters for this system. And SpeckleToolBox will list the data for the most recent measurements. These are color-coded, and the code here, for example, C means CCD or CMOS camera. HG refers to Gaia measurements. And you can find out what all these codes are from the Washington Double Star catalogue. Now, the other thing of interest here is that if you look at the orbital parameters and the plot, you can see here that this is plotted east here. Let's open this up a bit. East on the y-axis and north on the x-axis. If we go to the Washington Double Star catalogue orbit that you'll get with your file, you can see it looks a bit different. Let me just reduce that. I'm going to reduce this image. You do that by the scroll wheel on your mouse. If you move the wheel away from you, the image gets smaller. And if you move the wheel gently towards you, the image gets bigger. Now just be aware that this program does have a lag time, so just be patient in moving the wheel and allow the program to catch up. So looking at the orbit you get from the Washington Double Star catalogue, you can see that they look different, and that's because the axes are different. Here we have the north axis on the x-axis in SpeckleToolBox, and the y-axis is the east axis, but here in the diagram you get from the Washington Double Star catalogue, the x-axis is the east axis and the y-axis is the north axis. And so if looking at the SpeckleToolBox apparent orbit, if you rotate the image 90 degrees clockwise, then you'll end up with the standard view that you get from the Washington Double Star catalogue. Let's just close that. Now you should notice that the orbital parameters have been updated to the 2020 orbital parameters. Now you can add your observation to the data points present on this apparent orbital ellipse, and you do that by adding custom observation file. Now this custom observation file is your observations, and they should be put into a file like this, an Excel file. I've called it Dunlop 5 added observations. If we open that with Excel, you can see it's a simple Excel file which has the date, decimal date. It has my position angle and separation. Let's just those out a bit. It has the aperture of the telescope that I was using. I was using the Los Combros Observatory here. There's my reference, RJ LCO, and the technical code C is for photography. And you notice here that the date is 2024.895. Now what we can do is we can find out where, according to the orbital ephemeris, it thinks the secondary star should be for 2024.895. So we can just put the date in there, we can generate. And this blue square is where, according to the orbital parameters, the secondary should be in the orbit compared to the primary for decimal date 2024.895. All right. So now I'm going to add my custom observation file. Just going to close that up. Don't need to save it. I'm going to add that observation file. And you'll notice there's a little green square that's appeared when I added that observation file. So let me magnify this. So again, bring the wheel up, roll it towards you, move it around. Just be patient, there is a lag time with this program. And this is where it thinks the secondary should be for that date. And this is where my measurement is for that date. Now, if I just hover over that and right click, you'll see that it's got my date here, my identifier, the method I took, and it's got the measurement that I had of a separation of 11.321 arc seconds and a position angle of 184.65 degrees. And these are other measurements taken by other people. So this one here, for example, this was the last measurement on which the orbit was based, and this was in 2019.732 by NAP. And there are other elements here as well. For example, this one here was in 2010. This is a micrometer measure. All right, so let's just reduce the orbit in size down. So let's talk about optimization. I can only give you an introduction to optimization. It's a very complex topic, and there are a number of videos present from Boyce Astro with David Rowe about using this particular aspect of this program. As an introduction, what I would suggest is just leaving the weighting of the observations as they are. You can weight individual options according to how important you think they are, but that's a more advanced topic. What we're trying to do with optimization is to reduce what we call the WRMSD, or the weighted root mean square deviation, to a minimum value. The lowest value we can get. So here we have our proposed orbit with the new orbital parameters. I've added my observation taken in 2024. Remember, the last observation was back in, let me just check, 2019. And I'm leaving the weighting as 1, and I'm going to click Optimize. You can see that the value here is 282.038. And this program is going to run, it's going to use an algorithm, and you can see that a new orbital ellipse is being generated. You can see the old orbital ellipse is in blue, and the one that's moving is the new orbital ellipse. Now we'll let this program run for quite a number of iterations. How many iterations is debatable. when should you stop? These are topics that are covered in those other videos. But I'm going to let this run for a while, and you can see that the program is trying to fit data into what it thinks is the better ellipse. Now you can actually remove data. There might be some outlying points that are way out that you want to remove, and I'll show you how to do that in a moment. But we're just going to let this run. Why don't we go up to say 200,000 iterations of this program. You notice here that as it's running, the orbital parameters are changing here. So let's go up to about 200,000. Okay, we'll just stop it here. You can see the weighted root mean square deviation has gone down to 267.479. This is what it thinks is a better fit of the data. And these are the orbital parameters it's suggested that correspond to that ellipse. So let's just go back again and read an observation file. And we're going to calculate, we're going to generate that. I'm going to add my observation file here, which is just going to appear just there. Now, you can edit some of these points if you like. For example, this point out here looks like an outlier. So what you can do is just hover over it, right click, and you'll notice here there's an option of don't use in optimizer WRMSD. So you can click on that and a blue circle will appear around that data point, and that data point will not be included in the optimization calculation. And there may be some other outlying ones that you want to remove. Let's have a look at this one, for example. We could maybe remove that one. Okay, so let's now optimize. And again, you can let this program run for as long as you like and try and get the minimum WRMSD value, and that will be taken as the new orbital parameters. Let's just let it run up to 200,000 iterations. There's not much change in the orbital parameters there. Okay, I paused the video while I was allowing, just in the interest of time, the program to get up to about 200,000 iterations. And you can see here we have the suggested orbit in orange and the orbital parameters that are present there. So this is just a brief introduction into the Speckle ToolBox orbits and a very brief and superficial introduction into optimization. This program, I think, is very useful in showing you where your data fits into the other data that's present in your system that you're studying. Here you can see my data is looks pretty good. The distance from the prediction to my data point is about 94.16 milliarc seconds. So there are other videos present on this topic, and I refer you to them. So thank you very much for your attention.